Thank you very much. Before I get started, I learned an important lesson this week. And it turns out, if you are the second to last speaker at a conference, then the thing that you're going to talk about, a lot of people might have talked about that same thing already. But that's okay. I think we can still learn some stuff, and thank you to Miguel for kind of giving a really nice intro into my talk. We didn't plan it, but it worked out okay, or we'll see if it works out okay. So I'm going to be talking about functions. As Louis said, I'm Josh Abernathy. I work at GitHub on the desktop apps. So while you guys are like making cool iPhone apps and watch apps and like TV apps and like apps for your whatever, I'm making apps for your computer, which is still something people do, it turns out. But I'm going to be talking about functions and how much I love functions. But before I talk about functions and how I love functions, I'm going to talk about Legos and how I love Legos. Like a lot of people my age, I think we all played with Legos as a key part of our childhood. That was a defining part of my childhood for, I don't even know, 6, 7, 8 years, was just playing with Legos. And it wasn't until very recently that I learned some about the history of Lego. I have 2 kids. My youngest was 1 at the time, and she was sick. And I was up in the middle of the night, and because she wasn't sleeping, and so I wasn't sleeping. And I did what any parent of the 21st century does when you're awake with a sick kid at 3 a.m. And I went to the internet, and the internet gave me some entertainment to watch at 3 o'clock in the morning, and it was about the history of Lego. And it was really interesting. It turns out the original Lego brick looked like this, and it might be hard to see because of the contrast, but it has the nubs on top that we're all familiar with. But then underneath, it was completely hollow. So you could stack Legos on top of each other. They were like bricks, and they would kind of hold their position because you had the nubs, and the nubs kind of fit on the hollow part, but they didn't snap together like Legos do now. And that's like a big thing. That's the key to Lego, right? It wasn't until about 20 years after this original design, in 1958, that they added the tubes underneath the Lego, and that's what allows the Legos to snap together. And that was a game changer for Lego the company, but also just like Lego the brick. Because that meant that you could create these like ridiculous, amazing things out of Legos. Like this is a recreation of the Queen Mary, the Queen Mary in Lego. And at this scale, it's even hard to tell that it is Lego. But like you zoom in, and sure enough, it's Lego bricks. You got your like 1x2 bricks, your 2x4s. It's classic Lego. And maybe a more modern example of this principle is Minecraft. Minecraft is the Lego for the kids these days, I guess. But it's the same principle. You have these like really basic blocks, and you connect them, you snap them together, you put them next to each other, you put them on top of each other, and it turns out that these really, really simple principles can scale up really, really well to create just amazing, works of art, essentially. So this general principle, this idea that big things are made out of many little things, this works really well for Lego. This works really well for Minecraft. And it lets them create enormously complex things out of really simple building blocks. Of course, not everything is like that, right? Not everything in life is like that. You can have sculptures. And sculptures are more or less one big piece. Like down at a crazy level, there's, molecules and proteins and atoms and whatnot. But like at our human scale, this is one big piece. This has some downsides. You can imagine like the sculptor who made this. He makes this sculpture and he's super proud of it, and he shows it to his patron or his customer, and they're like, "Yeah, I really like that. I like the goofy look on the horse's face. Like that's pretty awesome. But I was really hoping that like the person would be standing next to the horse, and actually, could we make the horse like, I don't know, like a dragon or something?" And no, that's not how it works, right? The sculptor says, no, like I can't, like I'll take some more pieces of the stone off if you want me to, like I'll take a leg off or something, but the horse is not becoming a dragon anytime soon. Now, if it were made out of Legos, if this were made in Minecraft, it'd be like, yeah, okay, like give me a few minutes, I'll rearrange some pieces and we'll have a dragon. And that's kind of familiar, right? Because sometimes we make these apps, or we make these views or these screens, and then we show our product manager, or we show our customer, and they're like, yeah, that's a great screen, but I was hoping it'd be a dragon instead. And that's when we go into the corner and we cry and we pout, because it turns out we build apps a whole lot more like we're sculpting something. Like we're sculpting something out of UIKit with our blood, sweat, and tears. And then when it comes time to change it or fix it, we're in for some sadness. It doesn't work that way. We can't just take it apart and we can't just change the pieces around. It's one big unit. We sculpted it out of a single piece of UIKit, and we can't just change it. And this is a problem. This means that our apps are really hard to maintain. They're really hard to scale. And they're really hard to develop in the first place. We're here to talk about functions. I would say that functions are the Lego block of programming. They're this basic unit. They're this really small thing that we can use, that we can put pieces together, and we can make incredibly complex things. They're this small building block. And with functions, with these really, really small, basic things, we can make really, really big, impressive works of art. Because these things scale. Small things can be put together to make really big things. So, functions. I want to define what exactly I mean by functions, first off, because I'm going to use it in a bit more exacting sense than I think we usually use it. And then we're going to talk about, are our apps functions? Like, can we conceive of them as functions? Is that a reasonable mental model for us to use? And then we're going to talk about how we can start to use some of these ideas just in our code today, in the apps that we write today. So this is a function, right? Like it has the func keyword right there in front of it, so it must be a function. But I want to use function in a more precise way than this. Wikipedia, source of all human knowledge, tells us that a mathematical function is a relation between a set of inputs and a set of permissible outputs with a property that each input is related to exactly one output. And this is something that we probably learned at some point in our schooling, but probably most of us have forgotten it at this point. And this is a little overly wordy, so let's just say that functions are this consistent relationship of your input to the output. Like, if I have a plus function, it's relating two numbers to whatever the third number is, the addition of those numbers is. A function is a consistent relation, or a consistent mapping between two things. Is this a function in the sense that I'm talking about? It is, it turns out. Like this is a consistent relation of things. It takes a collection type. It's a method on the collection type protocol. And we give it a number, the number of items to drop out of the collection. And it gives us back a different collection, some subsequence of the original collection. So this is a relation between the collection, the number of things we're dropping, and then the resulting collection. And it's consistent. If I give it the same collection and I give it the same number of things to drop, it's always going to give me the same result. So it's a consistent relation. This is a function in the sense that we're talking about today. And it's really easy to reason about, because everything that we need to know about what this function does is right there in its type signature. We're giving it a collection, we're giving it a number, and it's giving us back a collection. And that's everything that we need to know about it. We don't need to know anything about like the internals of the collection. We don't need to know anything about how it works. All we need to know about are the arguments that we gave it, and that makes it really easy to reason about. It makes it really easy to test, too, because all the things that we need to give it are right there for us to see. And it's really easy to compose. It's really easy to stick that with another function. So we can drop some elements, and then we could map some elements, then we can filter some elements, and we can just chain all these things together. Just stick them all together, and they compose beautifully. So that's what a function is. But not everything is a function in this sense, right? And for lack of a better word, I'm going to call them funkies. Because they're these things that in Swift have this func keyword in front of them, and so we're led to believe that they're functions, but they're not really. We'll call them funkies. And this is a funky. Show view controller. Okay. Is it a relation? What's it relating? We have arguments, a view controller and a sender. Are those things being related in some way? Not really. Is there some kind of relation that comes out of this, right? We're talking about input and output. It's a consistent relation of input and output. Where's the output here? There isn't any. It's void. So it's not a function in the sense that we're talking about today. It's an abstracted unit of work, and that's fine. It's good to abstract units of work, but it's not a function. It's hard to reason about. We have to know a whole lot more to use that function. And if we wanted to test it, how would we even begin to test show view controller? Like we couldn't. We would have to know something about like how UI view works under the hood, and we have to know something about the view controller hierarchy. And that's just a bad time. So it's hard to reason about, it's hard to test. And can we compose it? Like, does it make sense to stick this together with something else? Not really. Like, there's no output to put into some other function. We could call it multiple times, but that's not composing it with anything. So that's a funky. That's in contrast to functions. Functions are easy to reason about. They're easy to compose. They're a consistent relationship of the inputs to the outputs. So functions are super cool, and I love functions. And they're easy to use in the small. Like Miguel gave us a really good introduction this morning to using them in the small. Like we can use them to do things like map, or filter, or flat map, or reduce. And that's good insofar as it goes. This communicates more of my intent to my fellow programmers. And it communicates more intent to the compiler or the standard library as well. So it's easy to use functions in the small for these sorts of things. But if we want to use functions in the large, if I want to use functions to make my app, how do I do that? Like if I'm starting a new app, and I'm writing some code, and I'm like, okay, we're going to make some functions here, and I'm going to make the run my app function. Like, how do I even do that? What does that even look like? What are my arguments, and what are my outputs, and like, what am I even relating? It's not really clear. Functions are not easy in the large. This is for a lot of reasons, but mostly we have to conform to the UIKit world. So we can't just do whatever we want. We have to function within Apple's frameworks. And that means that we have to bend to the way that they think about the world. Our app's functions. Our app's a relationship of input to output. What's this type signature? It's not entirely clear. But it turns out that there are some programs on our computers today that actually behave a whole lot like functions. And so maybe we can look at those and try to like take some inspiration from them. So the WC command line utility doesn't stand for water closet, like you Europeans might think. It counts things. It counts words, lines, characters, bytes. But we can write a type signature for this. We can say that the input is going to be some kind of string, and then the output is going to be an integer. And now we start to have a mental model for what this looks like. So even if it's not implemented as functions, we know how to model it as a function. this program can be modeled as a function. ls, also, we can think of this as a function. It takes a directory, and it gives us like paths or URLs or something. These are functions. And the cool thing about these programs is that we can compose them. We can stick them together, and we can make something that was more complex than what we had before. And it's super easy, right? We can pipe ls into wc, and we can find out how many files we have in our current directory. That's something that neither could do without the other. And because they're functions, we can pipe them from one to the other. We can compose them to make something more complex than what we had before. So we come back to my app. What is the type signature for my app? Right? We're going to write this awesome app that's going to count how many times I click a button. And it's going to be an OS X app, by the way, because all the cool people write OS X apps, not iPhone apps. But what is this type signature? What kind of types do we need here? What is our input? It turns out our input is a whole lot of things. Our input is touches. Our input is camera. Our input is all the sensors on whatever device we happen to have. Our input is whatever data happens to be on disk at the given time. Our input is the clock. It turns out our input is more or less the entire world, which is hard to model in Swift. But we can abstract this out, and we'll say that our input is going to be its state. It's some kind of state. In some apps, it'll be a bunch of things. In some apps, it'll only be one or two of these things. But generally, it's some kind of state that is fed into the app. So what is the output of our app? It's mostly UI. Most of the apps that we write are almost entirely about presenting something to the user. And there are some other things that'll happen, like we might make a network request, we might write something out to disk. That's also output, but mostly our output is UI, and that's a bummer because UIs are big, messy, mutable, stateful bags of sadness. Like, I don't know about all of you, but the UI code that I write is just shameful. It's just terrible, and it's bug-ridden. It's so hard to get right, and it's so hard to test. It's so hard to have confidence that you handle all of the cases that you need to handle. UIs are most of the output of our program, but they're also really, really hard. So we have a type signature now. We know that we're going to be taking in some state, some kind of state. And our output is going to be UI in some form. And this, we can think of this as a consistent relationship, right? This is a function in the sense that we talked about earlier. This should be consistent, regardless of like what else is happening. As long as we capture the state, we can always relate it to some form of the UI. It's a consistent relationship. It's a consistent mapping. Given the same state, we'll always get out the same UI. But our apps are different from command line utilities in a really key way. Because command line utilities run once, and they give you the output, and that's it. But our apps keep running, and they keep running, and they keep running, and they keep giving output. The UI keeps changing. So we need some way of saying that, like, whenever the state changes, I need to re-render my app. I need to update the UI. We're going to keep calling this over and over again. Every time the state changes, I'm going to recall render app, my render app function with the new state. And we're going to keep doing this and keep doing this and keep doing this over and over and over again. And it turns out that that gives us an app with a UI. Every time state changes, give me a new UI, and we'll put it up on screen. So, render app. We have a type signature. And that was the hard part, right? Basically writes itself. But at least now we have a mental model. We have a different mental model. We know how we can conceive of our apps as a consistent relationship between the input, the state, and the output, the UI. I said earlier that big things are made out of many little things. And that's why we love functions, because we can make big functions out of composing many little functions. And so our render app function, this is going to be a big function. Like if I'm rendering a whole app, that's going to be a big function. So it should be composed of smaller functions. We might have a render login function. It'll take some kind of state specific to rendering the login view. We might have render photos. We might have something lower level like render a button or render a vertical list. This is where composition comes into play, because we're taking a bunch of UIs and we're composing them to create one UI out of them by creating a vertical list. So we might have functions like this. Or we might have types, because it turns out that with some caveats, types are functions too. Every time I create a button with a title, it's a consistent mapping, a consistent relationship from like my title to a button. We could rewrite these as functions which create buttons, but the idea is the same, that these types are still just functions. And at this point, putting our UI together is just function composition, right? And we know function composition. We can do this. It turns out that UI is composition. And we already know this. Like when we create views for our app, they are composed of other views, which are themselves composed of other views, which are themselves composed of other views. UI is already composition in its nature. We just don't write it that way. And that's kind of silly. It's composition. It's composition all the way down. There's no reason that we shouldn't express our UI as the composition of functions, because that's what it is. It's composition. UI is inherently compositional. So we can make these big functions like render app out of many little functions. We can make big UIs out of many little UIs. So let's come back to the app that we're making. Remember, we're making an OS X app and we're counting clicks, and we know what our type signature looks like now, right? So we get a little further in writing our app. So application did finish launching, cool. Now we're going to do some magic, and we're going to say that like something happens, and we end up in the render app function. And this is the function, right? It's relating our state, which is the count, how many times we've clicked the button, to a UI of some sort. And that is itself composed of smaller functions. Every time that the click me button gets clicked, we update state in some way. Again, we're assuming that there's some magic here that makes this happen. We update state, and render app gets called again. And this just keeps happening and happening and happening. Now, as some of you probably already know, this exists. This model for writing apps, for writing UIs, this already exists, and it's called React. And it's kind of a joke at this point, but like every speaker has to get up here and talk about some Facebook open source project, because that's, I don't know what that says about the state of the art, but React is from Facebook, and it's a JavaScript library that lets you create HTML views. But it uses this very model of expressing your app as a render function which takes state and outputs UI. Facebook also created something called React Native, which is the exact same idea, but it actually outputs UIKit views. Facebook also created a library called ComponentKit, which is also very similar. ComponentKit is a little different in that it's actually written in Objective-C++. But it's more or less the same idea. And they actually use that in the main Facebook app. But for the sake of staying in Swift, for my example, I'm going to use a library called Few, which is one that I wrote, but I highly recommend that you don't use it, which is, of course, what the skulls mean. So please don't use this. It's more or less done as, like, check out what we can do. Like, this is entirely possible to do this stuff. So for the sake of completing this example, we're going to use Few. So let's come back to our app. This is how we would write that app that we kind of sketched out. This is how we would write it in Few. And I'm not going to get bogged down in the details, but it's remarkably similar to what we just kind of came up with on the fly. We have a render app function. and it's relating a component. This is a thing that holds on to the current state. It's relating that and the current state to an element, a UI element. There's some other stuff in there about like layout and other things like that, but this works. Our app is a function. It's a consistent relationship of our state. Our state is the number of times I've clicked the button to the user interface, and this works. Like, we have this awesome app. Probably going to win some ADAs, probably going to get some VC funding from this, because counting clicks is hard. But the point being is that our app is now a function. It's a consistent relationship. It's easy to reason about. It's composed of little pieces that are themselves easier to reason about. It's easier to test. These are just data structures. We can check that the data structures are what we expect they are. And this is all well and good. But the reality is that most of us aren't going to drop everything and start writing our UIs in React Native or Component Kit. And you're certainly not going to write them in Vue. So how do we apply some of these principles to the apps that we write today? There's a general principle that we can pull out of this. We can abstract this even further. And that is, we win a lot by separating calculation of a thing from the doing of the thing. And Andy Matuszak touched on this in his talk yesterday. He didn't explicitly spell this out, but this is more or less what he was doing. He was pulling out his logic of how to do a thing, or like what you want to do, from how it's actually done. If we want to use the nomenclature for this talk, we could say we're going to separate the function from the funky. The function is the interesting part. The function is the brains of the app. The function is the hard part to write. The funky is the boring part. It's the part it's assigning values to the user interface. It's super boring. And that's great, because the funky is hard to test. It's in your Vue controller, it's in your Vue, and it's super hard to test. But the function is easier to test. The function is just logic, and we can test logic fairly easily. We separate the function from the funky. We separate the calculation of the thing from the doing of the thing. And in that way, we gain so much power. React Native actually uses this separation to do all of the work on a background thread. Every time you render the app in React Native, it's on a background thread. And then it moves that data structure over to the main thread, because that's how we have to do it in UI kit land. But it has that flexibility. It has the ability to do this because it's separating the doing from the acting. I told you earlier I work on GitHub Desktop, and we actually have a pretty good example of this in the app. And I didn't write this, so I can't claim credit for it. For those of you who aren't familiar with the app, up at the top of the screen there's this graph, and it kind of shows you like how many commits you have and the difference between your branch and another branch. But we have to keep this graph up to date. And that's not trivial, because things that affect the graph can happen from anywhere. Like, a user could commit in the command line and then switch back to the app, and we have to update this to show that. So my coworker, Matt Deephouse, very nice guy, he wrote a lot of this code, and I can't claim credit for it at all, but it actually is a really elegant solution to this problem, and it embraces these ideas of separating the calculation of the thing from the doing of the thing. So this is all like, I'm kind of making this up. This isn't exactly what the code looks like, of course. But more or less, we have a graph structure. And this graph has the branches that we're comparing and a bunch of other data on it. But then we also have a graph update structure. And if I give the graph update, if I create it with an old graph and a new graph, it's going to figure out what has to happen to go from the old graph to the new graph. This has all the logic. This is essentially the function of the thing. This is the logic. This is the brains, is graph update. And so somewhere in our Vue model or some data layer thing, we call calculate graph. We make a whole new graph, and then we make a graph update. And then in our view controller or our view layer or wherever, we look at that update and we say, okay, I need to insert a new commit. I need to make a merge commit. I need to show a push happened. But all the logic, all the interesting pieces, all the hard pieces to write were up in this function, the graph update function, or the graph update type, which is a function. And so we did this. We separated the function from the funky. And it means that testing graph update and testing graph is super easy and super fast. These are just types. These are just functions. There's no UI involved. But it does all the hard stuff. And that's the important thing. We separate the calculation of the thing from the doing of the thing. The calculation is the hard part. The calculation is the part that will have bugs in it. The doing is the easy part. It's assigning things. It's almost just so mechanical that you don't even want to look at it because it's so boring. So that's how we can start to embrace functions, take some of these principles, and use them in our apps today. Before I finish up, though, I want to kind of end on a slightly different note. When we were looking at the example of command line utilities earlier, we looked at how we can compose ls and wc. Now that we have a mental model for apps as functions, can we do this for apps? Can we compose apps? Is that even a thing that makes sense? Like, can we think of Instagram as like the composition of camera and some filters? Obviously, it's more complex than that. But this mental model lets us start to think about, maybe this isn't so crazy. Like, at a different granularity level, this might actually be pretty reasonable. If I was writing my own app that was like a painting app or something, could my app be the composition of touches and then sharing to Instagram? It'd be awesome if I could write it that way. And this is kind of like, we get approximations of this with like sharing sheets and that kind of thing on iOS. But maybe this is a more foundational way to think about them. If apps are functions, then why can't I compose apps? Just like I would compose a function. But to be honest, there are a lot of unknowns. And I don't just mean in composing apps. I mean in treating an app as a function of UI, as a function of state to UI. There's a lot of unknowns. There's a lot of things that like people are still trying to figure out. There's a lot of imperative things that are hard to express in a function of state and UI. And in fact, I kind of glossed over this earlier, but the output of our apps is more than UI, right? It's writing things to disk, it's network requests. And how do we express those in our function? It's not clear. It's a lot of unknowns. But that's okay. Miguel talked about this earlier, but the fact is that we don't really know what we're doing when it comes to programming, and we don't do it well, and it's okay to not have all the answers. Like, it's okay to say, hey, I think maybe this is a better mental model for apps, but I don't know how everything fits together, and that's okay. We're still figuring this out. I remember when I graduated from university, I got a degree in computer science. I had this feeling that everything had already been discovered. Like Knuth and like those guys kind of figured it all out, like back in the 70s, and now we're just kind of like, we're doing it now. It turns out that's not at all the case. We're still really bad at this, and we're still figuring it out, and it's okay to try stuff, and it's okay that we don't have all the answers. Maybe don't tell your clients you don't have all the answers, but it's okay if we don't have all the answers. So that's functions. That's why I love functions. They're easy to compose. They're easy to reason about. They're easy to decompose. And those are all fantastic things. They let us build big things out of small things. And that's a very, very, very powerful principle. If you're curious to hear more about some of these ideas or related topics, again, Miguel talked about the Boundaries talk by Gary Bernhardt. He comes at it from kind of a different approach, but same ideas. He doesn't talk about UI so much, but a lot of the same ideas are there. A guy named Connell Elliott, very smart guy, has done some thinking about what it looks like to compose apps, to compose programs at the UI level. And he's done a talk and a paper called Tangible Functional Programming. I highly recommend you check it out. And then, of course, Andy's talk yesterday, Miguel's talk today, also great examples of some of these principles. And then most anything by a guy named Rich Hickey. I won't go into who he is, but he does some fantastic talks, and he's just an amazing speaker, and I highly recommend you check out anything that he's done. Thank you very much.
A great talk. Is there a way to transform your funky into a function? If there's example like if I touch 3 times, I need to make sure that something is happening, like represent a new view controller.
I don't know that there's a great way to extract that out necessarily. This comes back to kind of some of the stuff that Andy was talking about yesterday, which was that at a certain point, you have to decide that you're not testing UIKit. Like, we could test that every time I call a function, the state increments, and that's great, but I don't know that we even want to test the idea that, like, if I tap a button, the state changes. Because at that point, it's just like, well, is the AppKit team or UIKit team doing their job? And let's hope they are, if that makes sense.
Thanks.
Thank you, great talk as well. I wondered if you could, you gave an example about how to consider an app as a function, but are there some more things that you would say would initially you thought hard to think of as functions and then thought of a way to represent them as such?
That's a good question. This is one of those topics that's kind of been like rolling around in my head for a long time. I worked on reactive, or I still do some work on reactive Cocoa, but I made the first couple versions of reactive Cocoa, and part of the reason for that was trying to figure out this idea of UIs being functions of state. And so this particular topic has been rolling around in my head for a long time. So I can't say as there are other particular areas that I've thought about as much. I'll say that there are some other programming languages that try to capture this idea of everything that happens in a function. And at that point, you kind of start to capture this idea of functions being outputs of all the things that they do. So for instance, there's a language called Idris that tries to capture all the effects that happen in a function. And that can be writing a line to the console, that can be like firing off a network request. And that's probably a much more thorough and foundational way of looking at it, because you can actually express all of this stuff. But it's, pretty far out of the reach of most of us. So, all right, I think we're done. Thank you very much.